Hello my esteemed viewers. In this tutorial, we present clearly the foundations of engineering mechanics, a fascinating subject which will be studied across all students of all engineering disciplines. And of course, the statics and dynamics are among the first engineering topics encountered by most of the students. Therefore, we begin with a brief exposition on the meaning of engineering mechanics. Before defining engineering mechanics, we must consider the similarities and differences between physics and engineering. In general terms, physics is the science that relates the properties of the matter and energy, including excluding, of course, biological and chemical effects. Physics includes the study of mechanics, thermodynamics, electricity, magnetism, and nuclear physics. According to Accreditation Board of Engineering and Technology, aptly called as ABET, engineering design is the process of designing a system, component, or process to meet desired needs. And in this endeavor, engineering mechanics stands to be foundation subjects. On the other hand, engineering is the application of the mathematical and physical sciences to the design and manufacture of items. Design is the key concept that distinguishes engineers from scientists. Mechanics is the branch of physics that considers the action of forces on bodies or fluids that are at rest or in motion. Thus, engineering mechanics is the branch of engineering that applies the principles of mechanics to mechanical, civil engineering, aeronautical engineering, chemical engineering, and almost all allied engineering branches wherever designs are involved. And mechanics is the oldest of all the physical sciences, which we need to understand at the first phase of it, and it deals with the state of rest or of motion of bodies under action of forces. And mechanics can be classified with respect to matter that exists in three different states, that solids, liquids, and gases, fluids and gases. Their behavior, of course, under the action of forces vary. Therefore, we study them under different headings. Therefore, mechanics in the initial classification or in a broader classification, it can be classified into mechanics of fluids and mechanics of solids. And mechanics of solids may be further classified into mechanics of fluids and mechanics of solids, of course. Mechanics of solids can be further classified into mechanics of deformable bodies and mechanics of rigid bodies. And in mechanics of deformable bodies, which is going to be called as strength of materials or mechanics of materials, we bother about the resistances developed in the material inside the material of a component. As far as mechanics of rigid bodies are concerned, we just study the external effects of forces when a rigid body is applied with many number of forces, and we are concerned about its equilibrium and some of the establishment of some of the internal forces in the connected systems or rigid body systems. Mechanics of rigid bodies is further classified into statics and dynamics. Statics is, of course, the study of distribution and effect of forces on bodies that are at rest and remain at rest, and we derive equations of equilibrium there. Interestingly, statics also includes bodies under uniform velocity without any acceleration. Dynamics is the study of the bodies and their relationship with forces causing this particular motion. Dynamics is further classified into kinematics and kinetics. Kinematics is the study of motion of bodies without considering the forces causing the motion. It deals with relationship between displacement, velocity, and acceleration, and the things like that, and their variation with respect to time. As far as kinetics is concerned, it is a study of motion. It is a study of motion of bodies together with the forces. together, considering the effect of the forces conjointly, and that causes the motion. It relates the force and the acceleration by Newtonian laws of motion. And of course, we know that Newton laws were postulated by Isaac Newton in as early as 1686. And in order to, while studying the effect of forces on the bodies in engineering mechanics, either in the bodies being either in rest or in motion, the bodies are normally idealized. This idealization will make our analysis of forces or analysis of rigid bodies subjected to different kinds of forces a very easy procedure. So in order to ease out the entire procedure of analyzing the rigid bodies which are subjected to forces, we assume certain, or we make certain idealizations, and of course not at the cost of the actual results. Of course, actual results doesn't vary because we are concerned with the external effects of forces on the rigid body. We know that bodies are composed of molecules, and there is intermolecular attraction between them. Moreover, there could be voids and spaces in a body. Of course, the degree of molecular attraction depends upon voids and spaces present. And here, of course, this cannot be, this particular object cannot have such an intermolecular attraction as that of this steel plate, as that of this steel ring, and as that of this automobile part, and as that of this wooden beam, and so also the sponge. And therefore the degree of intermolecular attraction depends upon the voids and spaces present. For instance, in case of solids like steel or wood or whatever, the intramolecular attraction is stronger. However, for all analytical purposes, bodies, whether they are solids or fluids, are always idealized to be in continuum. Therefore, continuum provides a point or a kind of an assumption which makes us possible to study some of the principles, or some of the principles that are evolved in engineering mechanics will be applicable if and only if this idealization is made. So continuum in gist may be defined as the bodies will have continuous distribution of matter without voids or empty spaces. Another concept is rigid body concept. Of course, solid bodies, upon the application of external forces, may expand, may contract, may bend, twist, rotate, or show lengthier. They become lengthier. There may be elongation, there may be compression, things like that. And together, in a common word, they are termed as deformation. So deformation will include expansion, contraction, bending, twisting, rotation. Okay, and this kind of deformation will always develop what are called as internal stresses or internal reactions or internal resistances. If we are interested only in external effect of the forces on solid bodies, usually these deformations can be neglected. And this can be neglected when compared to the large size of the bodies. For example, here a stool or a bench or a chair is subjected to a force, it will be simply lifted, that's all. And here it is rotated, and the rotation matters over here. And here two people are just pushing this particular big box, and they will definitely get a resistance from the bottom, which is the frictional resistance. And here it is verified what is the amount of force that is to be applied in order to push, encountering the frictional force that is being developed over here. And here this is a best example of a rigid body. And the rigid body concept is, if you consider any line before application of the force, let us say line AB with a particular length, this idealization of rigid body will pave the way to to assume that even after the application of the load, the length of the line AB, which was drawn before application of the force, will remain unaltered. And this is the beam as far as the equilibrium and as far as the external reactions received by this beam is concerned at the supports. Rigid body concept will really help us while analyzing or while finding external reactions which supports is going to offer. And here also the chain will be subjected to some kind of a friction while it rotates, and it is the amount of friction that is required, or it is the amount of friction that is generated can be easily computed by assuming that the entire system is rigid. And the another concept is if we consider, let us say, the particle concept, particle idealization. If we consider the motion of a cricket ball in its trajectory when it is hardly hit by a bat, or motion of a shot put, motion of bombers, let us say, spilled out by a plane, motion of celestial bodies, we are interested only in the translatory motion, that is horizontal motion, maybe vertical motion. We disregard, in the melee, we disregard the spinning effect, the rotation, self-rotation, the rotation with respect to its own axis. Let us say spinning can be defined that way. Disregard this. If we disregard this effect, this assumption is justified, as the size of the ball is very small, size of the shot put is very small when compared to its own trajectory. Under such conditions, or under such circumstances, instead of considering the motion of the ball as a whole, we may consider the motion of the particle in the body to describe its motion. And we will consider the entire ball to be a particle, even celestial object to be a particle, and the bombers to be particles. The shot put is also a particle. As far as analysis, as far as the kind of trajectory traced and the kind of the initial momentum or initial velocity that is required, and how long it will move, where it's going to hit the surface of the earth, and what is the nature of the trajectory that is being traced. All these things are a matter of concern. For this, it would suffice if we assume this particle, this body, however big it is, to be a particle, because since with considering the size, the motion of the particle becomes huge. The path traced by the particle will become very huge, and if there is no rotational motion involved, because if there is no rotational motion involved, the displacement of every particle in the body is the same, because there is no displacement, because everywhere the body moves, the particle moves, and every other particle adjoining this, constituting the entire body, will also experience the same kind of displacement. Therefore, this idealization is coming to be called as particle idealization, and it doesn't hamper any of our calculations, any of our analysis when we take up analysis of point-like rigid bodies in mechanics. So in mechanics, a particle is a small localized object to which can be ascribed several physical properties such as volume, density, weight, etc. And force is a excellent concept. And as far as force is concerned, a typical fundamental definition of a force is a push or pull upon an object resulting from the object's interaction with the another object. Whenever there is an interaction between two objects, there is a force upon each of the objects. Forces only exist as a result of interaction. A force is one that can alter a body under rest and a body under motion with uniform velocity. And here is the forces that is exerted by these two people, and it will generate reaction. And of course, in nature we cannot see the force with an arrow, with a arrow tip and arrow tail moving in a particular direction. We cannot just visualize a force as it is, as such, and its effects can only be seen. The effect of a force can only be seen. And these two people are just pulling this particular rope, and it is shown in the form of these forces are seen in the form of a tension in this particular rope. And here a fellow is pushing this and a fellow is pulling this in order to make a movement, and the movement is the effect of these two forces. And if a ball is hit by a bat, let us say, a force is imparted, and this is also called as impulse, because if a force is applied for a short duration of time, it becomes an impulse. Anyway, force is applied to the ball, so ball will move. The movement of the ball is seen as an effect of the force. And here a nail is pulled from its fastening, and here we need to apply a force in order to pull it out, and the effect is the nail coming out. And here there is a spanner attached to a nut, and if you apply the force over here perpendicular to the axis of this spanner, and the effect is seen in the form of rotation of this particular nut. So rotation is the effect, force is the cause. So force will remain to be cause for certain processes. Therefore force is defined as basically as a push or pull. As far as mechanics is concerned, this definition holds good. Active force and reactive force. Active forces are external forces. Reactive forces are the reactions developed to resist the active forces. And active forces must be always equal to reactive forces in order that equilibrium will be sustained or equilibrium will be established. And here is a van of a particular weight, weight is the active force, and this van is going to generate reactive forces at the interface of road and the tire. Here there is one reaction, here there is another reaction. The reactive forces are the cause for this reactive forces happens to be the weight, which is the active force. And here a person is sitting on a stool, and he will impart his weight, and the stool will oppose his weight or resist his weight by showing a kind of a reaction opposing this particular weight. And here this is the bearing of a roller bearing of a bridge, and the bridge weight will be equally distributed, uniformly distributed over the supporting system through this bearing. Therefore bearing offers a reaction against the applied load or the load that is surmounted on it by the superstructure of the bridge. And here people are pulling this in a tug of war. This is the rope, and they are pulling 1 2 3 4 5 6 7 people are pulling along the same direction with various intensities of forces up to their capability. And if they are able to stretch out and they will be able to pull their opponents, and that is the effect. And effect is seen in the form of huge tension in the rope. And active force is their pulling, and the reactive force is the tension that is developed in the rope. And here is a supported system. There is a beam and there is a prop, and here is an active force that is applied. Active forces are situation specific. They are the demands. And if you want to construct a column, let us say column is going to weigh certain thing, okay, and the height of the column is decided by the situation, whether it is an industrial building or whether it is a residential building, and so also the length of the beam. And depending on this particular system, depending on the intensity of the load that is being applied, several components will develop certain reactions. Of course, the support will develop support reactions, and this prop will develop a typical compressive reaction. And here there is a crane is lifting a huge weight, and huge weight itself is the external force, and the tension developed in the ropes, the steel ropes or steel wires, are the reactive forces. Therefore active forces and reactive forces coexist in a system that is in equilibrium. Characteristics of a force. Of course, how exactly a force is characterized? Of course, four different characteristic features will define a force completely. Its magnitude, its direction, its point of application, and the sense. Here is a rigid body which is supported on the floor, let us say, and there is a force that is applied which is equal to 50 kilonewton, that is a magnitude, and the direction is 60 degree with respect to horizontal. Point of application here at this particular point. This is the point of application. And the sense is whether it is pulling or whether it is pushing. As far as this is concerned, it is trying to push this particular rigid body. And here is another example, and here this is the point of application. This person is trying to push this box along horizontal direction. Therefore, he is creating a force of 10 Newton along horizontal direction. This is the magnitude of the force. Of course, in order to represent this, we can plot this arrow to a scale. Let us say something like 1 centimeter equal to 10 kilonewton or 10 Newton, something like that. Okay, it becomes a vectorial representation. Direction is horizontal, magnitude is 10 Newton, and point of application is this particular surface, and the sense is pushing. There is a very important principle that should be remembered and which will be used in the entire engineering mechanics related topics. And here is a rigid body, and we will apply the force over here. The principle of transmissibility says that a force can be placed anywhere along its direction if the magnitude and direction is maintained as it is. This force can be moved anywhere along its line of action. Its effects remains to be same. And anyway, the condition is it should be placed along the line of action, and its magnitude should be equal to the original force which was there over here. And it can be said the other way also. This is the classical definition of principle of transmissibility. The conditions of equilibrium or principle of transmissibility is defined as the conditions of equilibrium or motion of a rigid body remains unchanged if a force acting at a point on a rigid body is replaced by the force of same magnitude and direction but acting at different point, provided that the two forces have same line of action. And here is a rigid body. This is the original force which is applied along this line of action. This should be equal to a force of same magnitude which is acting along the original line of action of this particular force. This system and this system are equivalent. And we will make use of this principle of transmissibility at a very simpler instances. Okay, and as we go down the tutorials, we will be able to understand how exactly we make use of this principle of superposition. And here is a box or a cubical element, and horizontal force is applied from this way. As far as this particular situation is concerned, this is a push and here it is a pull. Anyway, the same amount of force, same magnitude of force is placed it over here, but along the line of action. This has a pushing effect, this has a pulling effect. And here there is some kind of an L type of a section, and here originally it comes with a force somewhere over here. For some reason we can just move this force along the line of action to be and its however its point of application is changed. It's acting over here. As far as the external equilibrium of this L section, the placement of this load along its line of action anywhere along this line of action doesn't matter, doesn't alter the final results. And here is a ball, here is a sphere which is subjected to forces in this direction and in this direction, and we will just move them so that they will interact, they will make a confluence, they will get concentrated at a point in order to represent some kind of a concurrent force system. And for the sake of making it concurrent force system, we have just moved this, and our further analysis becomes very much simplified. So principle of transmissibility is of great help when we analyze the force systems, when we analyze particularly concurrent force systems, and in friction problems we will make use of this principle largely, and while analyzing the equilibrium of systems we will make use of this principle. And as we go on over tutorial after tutorial, we will be really able to understand how exactly the principle of transmissibility will be pressed into service. And here is another example where a beam is loaded from a load acting above the beam, and however there is an arrangement of hook over here, and this load can be simply transformed, and it can act over this hook. It can be hanged to this particular hook, and but as far as the support reactions are concerned, this arrangement of load and this arrangement of load have the same effect. This is in essence the principle of transmissibility of forces. Of course, whenever a rigid body is subjected to more number of forces, more than one force acting in multiple directions with different magnitudes, it's better we make it to belong to a particular system, and we draw the procedures available applicable to that particular system for the analysis. Therefore, whenever more than one force act on a rigid body, they are said to constitute a system of forces. The system of forces can be categorized into a big tree, a system of forces, and it can be coplanar forces and non-coplanar forces. And so in coplanar force category, it could be collinear forces, parallel forces, concurrent forces, and non-concurrent and non-parallel forces. And we have to attach coplanar, collinear, coplanar parallel, coplanar concurrent, and coplanar non-concurrent and non-parallel. The essence of coplanar forces is that any system, any real world system subjected to some kind of a forces which can be sketched on a plane of sheet of paper, plane of blackboard, plane of the monitor screen, if the situation can be captured on a two-dimensional plane, it becomes coplanar. And non-coplanar, it comes in the wake of the analysis of forces in space, forces acting in space, 3-dimensional, 4-dimensional, or n-dimensional space. And accordingly they can be categorized into non-coplanar collinear, non-coplanar parallel, non-coplanar concurrent, non-coplanar non-concurrent, and non-parallel forces. This is for the, so in essence the gist of this classification is, whenever a problem is given to us, whenever it becomes necessary to solve a problem related to engineering mechanics, first of all, the first task that the engineer should do is affix this particular problem into a particular system, and we can draw the methodologies available, the methodologies which are tailor-made and which are applicable for such a system, and we can solve that problem very easily. So this is coplanar collinear force system, because he is applying one kind intensity of force, this fellow is also applying, it is unidirectional, but it is going on the same line of action, therefore they become, and the entire process can be sketched on a Cartesian space, on a sheet of paper, on the blackboard. We can just draw a line showing line of action, and we will apply arrows like this along the line of action. Of course, the length of the arrows or magnitude of these forces may vary depending on the forces applied by these particular persons. Right, and here is another coplanar parallel force system, a typical beam loaded by parallel forces F1, F2, and Fn, and here is the reaction. They are also parallel. Of course, they are unlike parallel forces. One is going up, here it's going up, they are coming down. Anyway, in general, they represent coplanar parallel force system. It is not required to write a three-dimensional figure of a beam and apply the forces. It is enough. Because we can capture this particular scenario of a beam that is being loaded by parallel forces on a sheet of paper, and this is called, in essence, it is called as plane of bending and plane of action. So here are the active forces and here are the reactive forces, RA and RB. They are the reactive forces, and here it is coplanar concurrent. This may be a joint of a truss or joint of a frame, and here there are forces coming towards this particular joint. There are tension forces, compression forces, but anyway they are all concurrent. They are acting towards, they are converging towards a point. And here there is a lighting system that is being hung to this hook. The weight is the active force and the reactive forces are concurrent, and they will show off in the form of tension in the chains. So this system can be simply categorized, simplified by what is called as system of forces, and whatever the methods available to solve a problem under concurrent force system can be drawn, and this problem can be solved. That means solving of the problem means we can calculate tension in this chain and in this chain, in all the 4 chains, sufficiently accurately. And here is another example of coplanar, non-concurrent and non-parallel force system. Here is a truss, maybe possibly serving as a supporting a railway line, or it may be supporting a let us say roofing system, and it is subjected to parallel forces, horizontal force and inclined force. So they are hanky-panky. And anyway, as far as the determination of reaction is concerned, it is categorized, and there are several other factors matter. Moments will be generated. Okay, and we need to consider horizontal force effects, horizontal force effects, vertical force effects, and it will all culminate into finding support reactions at A and at B, and assuming this system into coplanar, non-concurrent and non-parallel system will pave the way to picturize this particular situation on a sheet of paper. Therefore, they become coplanar. And here they are all non-coplanar, collinear system. This represents there is an object, cubical object, and here there are two collinear forces, and of course if this is z dimension, z direction, and this is positive x and this is positive y, this is definitely xz plane, and this is let us say yz plane. This plane is yz plane, and this is once again xy plane. So xy, there are 3 kinds of planes which are mutually orthogonal, and the forces are acting in a collinear fashion, and they are non-coplanar. We can't afford to write such a figure like this. Okay, writing a 3-dimensional figure on a 2-dimensional plane of paper or a 2-dimensional blackboard is pretty difficult, and whatever we have written is a kind of an illusion. And here these are all non-coplanar parallel forces, and they are acting on this plane. These 2 forces are acting on this plane, and these 2 forces are acting on this plane. Non-coplanar parallel. And here non-coplanar concurrent, because if you project all these forces, they will meet the mass center or the center of gravity of this particular body, and they constitute, however, non-coplanar concurrent force system. And here is another system, non-coplanar, non-concurrent and non-parallel forces. Some of the forces are going like this, and some of the forces are inclined, but they are acting on all the surfaces, and it's a 3-dimensional force system. Anyway, these forces are supposed to act on 3-dimensional space. Therefore, they cannot be, and analyzing such a force system is pretty difficult, and it will be studied in the higher echelons of engineering mechanics. And in summary, we have come to the end of the end of this particular tutorial, where we concentrated some of the foundation aspects of engineering mechanics. We defined as to what engineering mechanics is. Then we brought out the branches of mechanics, and we defined the force as to what force is, and we have explained as to some of the idealizations and how they will make us, this idealization assumptions will make our life less miserable when we start analyzing a mechanics problem or solving a mechanics problem. And we have also explained principle of transmissibility, and we have understood not to the fullest extent as to how this principle of transmissibility can be applied at various locations while solving engineering mechanics problems. And we have also understood the rigid body concept, principle of transmissibility of forces and force system, and the necessity of categorizing the force system under different headings. With this, we have come to the end of this particular tutorial, and in the next tutorial we will start to deal with analysis of concurrent forces. And until then, bye. And if you have liked this video, kindly subscribe to this tutorial. Until then, bye. Thank you for your patient viewing. Thank you.